An important service provided by TCP is congestion control. Before exploring TCP congestion control, in this section, we will first learn what is congestion. We will first briefly discuss how it happens and why addressing it is important for a reliable transfer protocol. Congestion is experienced by a packet in a network when routers used along the path to the destination within the network have more traffic than they can handle. Therefore, their buffers grow longer due to high traffic intensity and eventually overflow. As a result of this, we experience packet delays and losses. You can think of congestion as something that happens when too many sources send too much data too fast for the network to handle, and therefore they clog the network. We learned what to do to manage the reliability of transmission in a communication when loss and delays happen, with mechanisms to retransmit lost packets and ways to solve out-of-order reception due to delays, and delivering data in order to the application layer. But we haven't learned how to alleviate the congestion problem for the network, so it won't affect our packets as much. There are ways to perform congestion control, with controlling the amount of data a sender sends into the network. But first, we need to take a closer look at the congestion itself to better understand the solutions for it. Please note that congestion control is different from flow control. In flow control, sender controls the rate of transmission so that it can prevent overwhelming the receiver. In congestion control, the sender will try to control the data it's sending to avoid causing congestion within the network on the path to destination. Let's examine a few simplified scenarios to better understand the source of congestion within the network and its effects on the performance. In the first scenario, we consider two senders and two receivers that have data connections. Their communication goes through a common router, which is on both of their paths. Also, assume that the router has an outgoing link capacity of R and an infinite buffer. Assume both of the senders are sending data at the rate of lambda n bytes per second. Since there is an unlimited buffer in the router, with increase in the rate of transmission from the sender, the queue at the router will grow, but will not drop any packets. Therefore, there will be no losses and no retransmissions. And with transmission of lambda n bytes per second at the source, we will receive the equal value of lambda out bytes per second in the destination. Assuming both of the senders are sending at rate lambda n, the graph in the figure shows the per connection throughput for each of these connections. With the increase in the lambda n, the lambda out received at the receiver side will increase until the transmission rate reaches half of the outgoing link capacity of the router. Since the two connections are sharing this link, and it will be at capacity at this rate, with increase in lambda in, the lambda out could no longer increase. Both of the connections will keep the same share of the throughput, which is half of the link capacity R from that point forward. The delay, though, will increase substantially as the sending rates use the link at capacity. So, we see that even with infinite buffers, congestion will result in increased delays.